The chapter title for Chapter 16 is Planar Kinetics of a Rigid Body. I always like you to know where you are in this process. If you haven't read Chapter 16 yet, please read it before lecture on Monday. It'll really help you get a good understanding of what's going on. So let's just talk about what this means. What does planar mean? On a plane. How many dimensions are on a plane? 2D. We're basically talking 2D now. Kinematics. Okay, I've asked you this several times in class. I want an answer this time. What does kinematics mean? How things move. Very good. Geometric aspects of motion. And just a reminder, what I mean by that is that we're looking at how things move. Their position, velocity, acceleration, not why things move. We're not looking at any forces yet. Okay? Rigid body, what does this one mean? But that's not really the big meaning for us. That there's no deformation. That's what rigid body means. But to be honest, we are in rigid body mechanics, which includes statics and dynamics. So we know that already. The real big news for us is what is a rigid body, or what is a rigid body not? A rigid body is not a particle. What this means to us is no more particle assumption. And what does that mean practically? Spinning. It means rotation. Because if we have a particle, it's going to act the same whether it's rotating or not. If we have a rigid body, and we throw a stapler across the room, which is always fun, it doesn't just fly like normal with no spinning. There's rotation, and we have to take that rotation into account. Thank you. Okay, so types of motion. There are 3 types of motion. There's 4 types of motion listed here. The first one we started off with, you notice this object is just going straight in a straight line. We call this rectilinear. This is rectilinear motion. The next one, we have the object, and it is going on a curve, which is the name of the type of motion. Is it rotating? It doesn't look like it, right? That line, the black line, is vertical in both situations. This is curvilinear motion. And we already learned that too. Both of those, rectilinear and curvilinear, we can identify all of the motion by the motion of the center of mass, right? Because there's no rotation. So the center of mass is moving just like the rest of the body. They're all moving the same. Okay, down here is rotation, or sometimes called pure rotation, because there is no or rotation about a fixed axis. There's no translation going on. And then finally, what we're trying to get to is the next one. There is translation and rotation. It is the stapler flying across the room. That is most motion, and we just call it general planar motion. Okay, we have learned rectilinear, we have learned curvilinear, and we are going to learn rotational right now, today. And then we will add those 2 together to get this. Okay, the nice part is that we just learned relative motion. We just did a very detailed problem in relative motion. Relative motion is the foundation of everything we're going to do in rigid body motion. So this isn't something new. Just as a reminder, our equations for relative motion, they come from a fixed and a translating coordinate system. In a little bit further in Chapter 16, we're going to have a fixed and a translating and rotating coordinate system. Why? Because it's easier to solve some problems that way. So we're going to have a fixed coordinate system. We're used to that. The translating coordinate system is moving at any point on the body. Okay? So we're taking the concept that we just learned, which is we have a translating observer and we have a fixed observer. Now we're throwing that translating observer on the stapler. Okay? That translating observer is some point, somewhere on the stapler as it flies across the room. B is another point on the stapler. And we have the person on the stapler looking at B and saying, what is my relative position, relative velocity, and relative acceleration to the other point on the stapler? Why is that important? Well, if it's spinning and flying through the air, you'll know. because there's going to be some change in the relationship here. Then we have the fixed observer observing both points. And we know that we can relate those three by a simple tip-to-tail triangle construction. And we know that RA plus the position of B with respect to A is going to be equal to the position of B. We could also write that the opposite way. The position of B plus the position of A with respect to B is equal to the position of A. Either one of those equations is super helpful. Notice the pseudo-canceling that works in both of them. I'm going to take the second one and take the derivative of it, and we get the velocity of B is equal to the velocity of B plus the velocity of A with respect to B is going to be equal to the velocity of A. And then the acceleration of B plus the acceleration of A with respect to B is equal to the acceleration of A. We have three relative motion equations that relate position, velocity, and acceleration. Okay, let's relate that to the types of motion that we've already learned. Translation. Pure translation is both rectilinear and curvilinear. Okay, so if we have rectilinear or curvilinear motion, let's go back to this page. These are the first two. Notice that there are 2 points on each one of these. If I'm the point up here, and I'm looking at that point, I'm on the body, flying through the air, but I'm not looking around. I'm just looking at that one point. Is it moving in relationship to me? Is the relative position changing in any way? No. I'm on this side of the stapler. It's going like this, flying through the air in curvilinear motion. Notice it's not rotating. And I'm looking at another point in the stapler. To me, nothing's happening. I'm on the body moving, nothing's happening. If I look off to the side, then I would start screaming. But as far as just looking at the body, nothing's happening. So what that tells us is in our equation, the position of A plus the position of A, or B with respect to A, equals the position of B. When I take the derivative of that, I end up with the dRA dt plus d position of B with respect to A dt is equal to d position of B dt. Both of the points are moving. And since both of the points are moving, both of these are not zero, because the absolute position is changing. But the relative position of one with respect to the other is not changing in translation. So that would be zero. And we end up with velocity of A equals velocity of B. In translation, the velocity of any point on an object equals the velocity of every other point on the object. In translation only. Does that make sense? That's why we could use a particle assumption. In pure rotation about a fixed axis, it would be the opposite. The relative position of B with respect to A would not be zero. But the relative position of the fixed axis would be. The change in position of a fixed axis is zero. So let's talk about rotation. The really nice thing about rotation is you've already learned all of it. You just didn't know you had. All of the same equations apply to rotational motion as they do to translational motion. I'll give you an example. Give me a kinematic equation that we've learned. There's 3 of them. Give me one. Acceleration equations. V equals yes, gt. Okay. In rotation, omega, which is angular velocity, equals d theta dt. Similar, right? The top one says in translation, velocity is equal to the rate of change of position. In rotation, omega is equal to the rate of change of angle, the rate of change of theta. Okay? Another one, acceleration equals dv dt. Alpha, angular acceleration, is equal to d omega dt. That's our second kinematic equation for rotation. What is the third kinematic equation for translation? A, starts off with A. Very good. ADS equals VdV. These should be, you should have these in your memory if you don't already. Those three are the most important equations, and these three we're learning now. Most important equations in this class. ADS equals VdV. Who can tell me what the rotational version of that is? Go ahead, write it down on your paper. Compare it to your neighbor. See if you got the rotational version of ADS equals VdV. You're making your own equations now. You don't even need to teach. Alpha d theta equals omega d omega. Okay, so everything that we learned about the math and equations for translational motion holds for rotational motion. This is pure rotation about a fixed axis. What does that mean? Well, we have a few pictures here that I'd like to explain. So we use our right-hand rule for rotation. The right-hand rule, just like we learned when we learned moments in statics, you put your right hand here with your thumb pointed up. Your thumb is the axis of rotation. Okay? Thumb is the axis of rotation. Positive rotation is the way your fingers curl. Negative. This is how I always remember it. Negative rotation, if you bend your fingers back, ouch, that hurts. That's negative. That's how I always remember it. So you got your thumb up. This is d theta, change in theta, acceleration, omega are all in the same direction. If you have a negative alpha or omega, it just means you're bending your fingers backwards. So it's negative. Okay, the next slide, as you'd probably expect, is constant angular acceleration. We can do the exact same math as we did in translation to find our constant acceleration equations. Is equal to d omega dt. We're going to start there because omega isn't necessarily constant. Acceleration is constant. This is why it's a constant angular acceleration. So we have alpha dt equals d omega. Integrate both sides, 0 to t, omega naught to omega. We know that alpha is constant, so we can take it out of the integration, and we just end up with omega times t equals omega minus omega naught, which gives us the equation omega equals omega naught plus alpha t. Hopefully that looks very familiar, and it reminds you of the equation velocity equals initial velocity plus constant acceleration times time. That is our first constant acceleration equation, and now we have the angular acceleration. We then use our second one, which is omega equals d theta dt. And we do the same thing, omega dt integrated equals the integral d theta from theta naught to theta and from 0 to t. Now I plug in the equation that I've already solved for omega, and I end up with the integral of omega naught plus alpha c times t from 0 to t is equal to theta minus theta naught, and that turns out to be 1/2 alpha c t squared plus omega naught t plus theta naught equals theta. Hopefully that reminds you of the equation 1/2 ac t squared plus v naught t plus s naught equals position. So we have two constant acceleration equations. Our third constant acceleration equation we solve the same way we did with the other one, and it is omega squared equals omega naught squared plus 2 constant acceleration times theta minus theta naught. That's our third constant acceleration equation, and we get it from alpha d theta equals omega d omega. So what I've just told you is that basically you can solve rotational motion problems using all the same math, all the same information that you had previously, except for now, instead of looking for a position, you're looking for a theta. Instead of looking for a velocity, you're looking for an omega, which is an angular velocity. And instead of an acceleration, you're looking for an alpha, which is an angular acceleration. All the same math applies. However, there's also a relationship between linear and angular velocity. To figure out this relationship, we are going to use a little trick that we've already used 2 or 3 times in this class. Hopefully you all watched it on the videos I posted, but let's talk about it real quick here. That trick is arc length. So arc length, if I have a circle of radius r, and I wanted to figure out what is the length of this arc within that circle, we're going to call that arc S. And we're going to say that we know the theta that sweeps that arc. Okay? So if I take that radius and I sweep it at an angle of theta, the end of the radius is going to move along that blue line a distance S. R theta equals S. That's the definition of arc length. We're going to use that fact that, and this picture over here to relate the rotational motion of this blue potato, which is just representing any rigid body. We have a blue potato rotating along this axis of rotation. You can see the arrow here, and you can see omega would be positive because it follows the curve of my right hand. So we know that we have positive omega. We have positive angular rotation. And what we want to know is how does that rotational motion relate to the motion of a point P? That point could be anywhere on the rigid body. But we want the absolute motion of that point. We don't want how is it rotating about its fixed axis. What's the velocity? What's the velocity of that point? If I was sitting at point P, how fast would I be going? To do that, we're just going to say if P starts off where it is, some unknown time later, it's going to be over here. And we're going to say it's going to move not very far. We're going to zoom way in and see it just move a tiny little bit. If that moves a tiny little bit, we're going to say the radius has swept a distance of d theta. In other words, it swept a very, very tiny piece of theta. And we want to know how far has that thing moved. What is my ds? My ds is the distance that it moved from one point to another as it rotates. And if we use arc length, I think you can see that ds is equal to r d theta. We don't always want to just talk about how many thetas we've done, like how far have we rotated. We might want to say, how fast is P going? In velocity, in translation. Okay, once we have that equation, we're going to divide both sides by some amount of time, a little tiny amount of time that we call dt. ds dt equals r d theta dt. Well, what's ds dt? Velocity. Velocity is equal to r. What's d omega dt? The rate of change of theta with respect to time. Angular velocity, which we call omega, right? Velocity equals r omega, about the simplest relationship that you could come up with. The velocity is going to be equal to omega, which is that angular velocity, times the radius. However far out, you're going to go faster and faster and faster as you get further and further away from the fixed rotational axis. Makes sense, right? Okay, that was a planar definition on a single slice of that plane. We can actually extend that to 3D using vectors. It turns out the vector formulation of this, as you'd probably expect, uses the cross product. Okay? The cross product just takes out the component of the vector that we need. The component of the vector that we need is that distance from the fixed axis. Our velocity vector, we say that's going to be equal to omega vector. Omega is a vector. It points in the direction of my thumb, right? We use our right-hand rule to identify the direction of omega, crossed with the position vector to that point. And I'm going to put a little p down here just to say that's the position of p. The nice thing about that position vector is it can be from any point on the fixed axis of rotation. The cross product magically will pick the component we need to make this turn out to be the same magnitude. For example, this rp here, that's one vector that starts from the axis of rotation and goes to the point. Another vector would be r. I could put that in here. I'd get the same answer. Another vector would be from here to there. It doesn't matter. As long as it goes from that fixed axis of rotation to the point, you get the same answer. So far, we've done a relationship between linear and angular velocity. Pretty simple relationship. The velocity is equal to r omega. Or the more universal relationship is that the velocity is equal to omega cross r, and that r is kind of a specific r. You can have many different ones, but it has to go from the axis of rotation, point of interest. Any vector from the axis of rotation to the point of interest, you throw it in that cross product, you'll get the velocity. Okay, that's velocity to rotational velocity, or angular velocity. What we want to do is we want to take that concept we just learned and extend it to acceleration using our kinematic equation. Acceleration is equal to dv dt. Next week, we're going to learn that this is a very important concept for any vector, not just a velocity vector, but any vector within a rotating coordinate system can be related to a fixed coordinate system using the same derivation. We'll talk more about that next week. But A equals dv dt, which is if we want our v to come from our rotation, we're just going to say that v as a vector is equal to omega cross r p, where r is the vector from the axis of rotation to p. We're going to plug that in. So we'll say acceleration is going to be equal to d omega cross r dt. So we're taking the derivative of a cross product. How we treat that is in the name. It's a cross product. So what rule would we use? Product rule, right? Cross product is a type of multiplication. Okay? It's a specific type, but it still follows all the rules of multiplication. So we can use the product rule for this differentiation. So we'll say A is equal to the derivative of one times the other. That would be d omega dt. The times is our cross product, rp, plus omega cross with the derivative of rp dt. Okay, what is this part of it? drp dt. V, very good. That's the velocity of point P. So we could say A is equal to d omega dt crossed with rp plus omega crossed with the velocity of p. But we can even go a little bit further. What's the velocity of p if we're looking at fixed rotation? First equation written on the page. Right? Let's plug that in. We just got that from the last slide. So we get acceleration is equal to, what is d omega dt? Angular acceleration, which we call alpha, right? So I'm changing my d omega dt to an alpha, crossed with the position, plus omega, crossed with our velocity, which is omega, crossed with position. That's how we relate acceleration to both angular velocity and velocity. Velocity is in the parentheses there. And initial position. This is a very important equation, and it's an equation that we'll come back to. As I said, you notice that what we're doing is we're relating an absolute vector. This is a vector, the absolute acceleration of a part, of any point on the object, to some relative vectors. Now, when I say relative, I mean vectors that exist inside our reference coordinate system. Our reference coordinate system is the coordinate system that's going to be moving along with our rigid body. Within that relative coordinate system, things happen. Things happen within that relative coordinate system like spinning and even sliding, where 2 points change the distance between each other. We need to be able to relate that to the real world. What's the real world? Earth-fixed coordinate system. That's what we're doing here. We're saying that in our Earth-fixed coordinate system, we can have vectors that are relative to our reference coordinate system. We're going to make that a little bit more general next week. For now, let's go ahead and look at this equation and see if we can learn a few things about it. The first thing is that we're in Chapter 16. This equation is going to be good for 2D or 3D. Because it's using vectors, it's using the full cross products. In Chapter 16, we're in 2D. So if we're in 2D, for 2D only, let's go ahead and look at omega cross r. Okay, in 2D only, what direction is our omega going to be in? If we have 2D rotation, and let's just say the plane we're looking at is an xy plane, what direction is omega going to be in? We get our right hand out, and we think of this piece of paper as our rotation. We have a plane. See, I'm looking straight down at it. We have a particle P, and there's some omega rotating this way. And that P is going along the outside of the object. It's going to be tangent to the plane, because you use the right-hand rule. The right-hand rule says use your fingers to show the direction P is going. The direction of omega is your thumb. Just like a moment, when you learn moments in statics. Okay? So if we have an xy plane here, let's say this is x and this is y. We've got our RP going out this way. What direction is omega in? Add the page, which would be z, right? So let's go ahead and rewrite omega cross r in 2D. We'd have omega cross with omega crossed with r. I want to write these in general terms. That r, we don't know what r it is, but does it have a z component if we're in 2D? No. So we're going to say r p is equal to rxi plus ryj. Omega is equal to omega k, because omega can only be in the k direction if we're in 2D. Let's go ahead and see what the cross product does to that. I'm going to keep these parentheses here. We're going to do that interior cross product first. If you remember how to do the cross product, I always like to do it this way, where we do I, j, and k on the top row. The second row is the first thing to be crossed, which is our 0, 0, omega. And the third row is our rx, ry, and 0. We take the determinant of that matrix, and we get our cross product. How do we take the determinant? Well, we cross out the column and row that I is in. Then we take the determinant of that 2 by 2 matrix, which is just multiply these two together and subtract these two multiplied together. So we end up with 0 minus ry omega, all of that times I. You guys with me? This should be review. And then we subtract, because it's j, we subtract the determinant of that 2 by 2 matrix, which would be 0 minus rx omega times j. And if we look at k, we get 0 times 0 plus 0k. So we end up with negative ry omega I plus rx omega j. Any questions about that? Okay, I'm doing something very longhand here that you're going to be able to use a shortcut for later. So this derivation will help us in the future. Okay, so now what I want to do is the second cross product, which is this omega crossed with what we just determined. Our second cross product would be I, j, k, and then we'd have 0, 0, omega, and we'd have negative ry omega, rx omega, 0. We're going to have 0 minus negative ry omega squared, I, minus 0 minus negative ry omega squared. Oops. The first one should have been rx. And there's no negative here. Let me go ahead and do the crossouts to show what I'm talking about. The first part there should have been 0 minus rx omega squared. And the second part is 0 minus negative ry omega squared, j. Okay. Very longhand, but we'll get to what we're trying to find in a second. Let's go ahead and just write this ij out. We end up with negative rx omega squared I. 3 negatives is negative ry omega squared j. If I factor out a negative omega squared, I get negative omega squared times Rxi plus Ryj. What is Rxi plus Ryj? Rp. In 2D, omega cross Rp equals negative omega squared R. Notice how that there's no harpoon on the omega, because that omega squared is just the magnitude. We take that magnitude of omega, we square it, we add a negative, we multiply it by our original R. It's in the same direction as our R because it has to be. It has to be in the same direction of our R because we're taking we're making a vector perpendicular to these two, and then making another vector perpendicular to these two. There's only one vector that's going to be perpendicular to the omega and the position vector, and that's the original vector. Does that make sense? Okay, in 3D, is it true? No. In 3D, you perform the cross products, and you get your answer as you would get it. You have to do both cross products in 3D because you don't have those zeros. The zeros are what make this happen. Okay, so in 2D, we've got acceleration as a vector is equal to alpha cross r minus omega squared r as a vector. One really interesting thing about this is directly related to the acceleration that we get in normal tangential. Alpha cross r. Alpha cross r is telling us that basically we're taking alpha, which is the angular acceleration, crossed with how far it is from that axis of rotation. Okay? So if you were that particle and this thing started rotating faster, it would make you feel like somebody just hit the gas, right? How far you are from the axis of rotation, it would be more or less acceleration. This component is tangential acceleration. Alpha cross r is their tangential acceleration. This is just in 2D. Yeah, the only thing that changes in 3D is omega cross r instead of the shortcut. So this is AT, and omega squared r would then therefore be what? AN. Omega squared r is AN. This is a very important equation. Make sure you have that written down. I suggest always writing this boxed one in the center, the 3D version, and then asking yourself, can I do the 2D shortcut? And then apply it if you can. If you memorize the second equation, then when you starting to do 3D, which we do next week, you're going to forget that you can't use that negative omega squared r. Okay, we have two different types of problem we're solving in our homeworks. The first one is rotation about a fixed axis. Remember, as I was saying, as we go up this higher level of learning, you do not want to memorize the recipe to solve problems. Instead, you memorize the procedure. Okay? Just like if you were a chef, you would not memorize recipes. You'd memorize the general procedure. I know how to cook pasta, and then I'm going to do something amazing with it, right? Same idea here. That's why I'm teaching procedures. The procedure for a fixed axis: establish a sign convention along the axis of rotation. This is just setting up your coordinate system like we always have. Do you want your axis of rotation to be positive out or positive in? I recommend using the right-hand rule. Find your x-y axis. Go from your x to your y. Your z's got to be that way. Okay? If a relationship is known between any of the two variables, alpha, omega, theta, or t, the other variables can be determined from these three kinematic equations. This step is identical to everything you've done in curvilinear motion. Okay? The only difference is we're using omegas, thetas, and alphas. If alpha is constant, use the constant angular acceleration equations, just like we did for translation. Determine the motion of a point. The scalar equations, v equals omega r, at equals alpha r, and an equals omega squared r, can be used. Those are scalar equations. The vector versions are down here, where velocity equals omega cross r. Acceleration is at plus an, which is alpha cross r, omega cross r. Yes. This is a different step than this, though. The constant acceleration equation is basically being used to move between position, velocity, and acceleration. In this case, theta, omega, and alpha. Once you know those, they might ask you, okay, now you know alpha, what is the linear acceleration? That's when you use this. So this is relationship between rotation and translation. That's just solving within rotation. Okay, let's do a simple example problem, and then I'll find a video of a more complex one that I can put online. Yeah, I think we can do this one. So next one, the motor turns gear A with a constant angular acceleration of alpha A, and I'm going to start my givens right away. Alpha A equals 4.5 radians per second squared, starting from rest. The cord is wrapped around pulley D, which is rigidly attached to gear B. Find the velocity of cylinder C and the distance it travels in 3 seconds. So we're supposed to find the velocity of cylinder C. So what's something that you notice right away? Is there anything that there's a little alarm going off in your head? I'm probably going to have to use the radius of the gears. Very good. Okay. Notice that there's an angular acceleration given, and they're asking for a linear velocity. Okay? So we know that we're going to have to use that relationship between angular and linear motion that we just learned. Okay, so how are we going to do this? Well, we basically trace the motion from what we know to what we want to know. What we know is over at A. So I know what A is doing. I at least know its acceleration. You have a choice. You can either translate that acceleration all the way over to D first, and then do your kinematic equations for D, or you can do your kinematic equations for A and then translate what you want for D, like velocity, right? What we really want to know is omega D. How do I know that? Because they're asking for VC, and VC is going to be the same thing at this instant as VP, right? Because this is an inextensible rope. So if P moves up 1 inch, C moves up 1 inch. Does that make sense? VC equals VP. And what does VP equal? Omega RD. Omega D RD. However fast D is moving, multiplied by its radius, is going to give us the velocity of P. You have to do some reasoning here and some tracing from one end to the other. So basically, if we can find omega D, we can find our answer. We have 2 ways of doing it. We can either find the velocity of A and translate that over to D, or we can translate over the acceleration and then do kinematics. Let's go ahead and do the first one I said. So we will look at gear A. So for gear A, alpha A is equal to 4.5 radians per second squared. Ding, 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 alarm bell just went off. What type of acceleration is that? Constant. We can use our constant acceleration equations. If I want my velocity, my angular velocity of A, that's going to be equal to my initial plus alpha A times t. Starting from rest is one of the givens, so my initial angular velocity of A is equal to 0 is one of my givens. So I can put 0 in here, and we end up with omega A is equal to alpha A times t. We're given t. T is equal to, I really screwed up the givens today too. T is equal to 3 seconds. So that's going to be equal to 4.5 radians per second squared times 3 seconds. What is that, 9, 13 and a half? Okay, so it's going 13 and a half radians per second. That's how fast A is spinning. Any questions about what I did there? How am I going to relate that to how fast D is spinning? Gear ratio. I heard it back there. Gear ratio, okay? How do we get gear ratio? Well, the way we get gear ratio is we're going to look at P, which is a point right there. We use P and P prime in this case. You can use whatever point you want. First, look at it from the left-hand side. What is the velocity of P if you just look at gear A? Omega R, right? Omega A, RA. Okay, for the same point, look at gear B. Look at gear B. Pretend like gear A doesn't exist. what would the velocity of P be relative to gear B? Omega B RB, right? So if that is the velocity of P for both equations, then I can say omega A RA equals omega B RB. I know omega A, that's 13.5 radians per second. I know RA is given as 0.075 meters, or 75 millimeters. And that's going to be equal to omega B times RB, which is given as 200. Notice that it's RB and not RD. It's given as 225 millimeters. Solve for omega B, and that would be 13.5 times 0.075 over 0.225. Whatever we get there, we now know how quickly omega B is spinning, the angular velocity of omega B. How is that related to the angular velocity of omega D? Do I need another gear ratio? Very good. It's the same. Why? Because they're rigidly connected together. If one spins, the other one has to spin. Okay? Look, think, reason to go through these problems. There's no recipe. You're not going to solve each problem the same way. You have to look, think, and reason.